Hi, my name is Sean Hyerson, and I'm a student at Oregon Institute of Technology, and my chosen project for Electronics 3 was photoplethysmography, or PPG. I decided to implement this as a portable device. I figured it would be great to have functionality and people can actually use it or, play with it, I suppose. The circuit is implemented via IR LEDs and phototransistors. There's two sets of them. Each set goes to an input of the INA 126 instrumentation amplifier, which the output signal gets fed into a high-pass Butterworth, 5-pole high-pass Butterworth, and gets fed into a 5-pole low-pass Butterworth for minus 100 dB attenuation. This filtering helps eliminate 60 Hertz noise from any electronic devices that are around you, any frequencies that are an outlier to your system or to my system that I designed. Here we see the TCRT 1000. This is the configuration that I use for the sensors. This is one set of the sensors used. So we see a phototransistor here right next to an LED, an IR LED. It was nice because there's a shield right between the diodes, and it helped eliminate some parasitic IR light. So here, this is just for visual representation. You have two fingers. Each finger is going to lay across one of these sensors. Also, it was nice to use these because these are the same sensors that we use for advanced microcontrollers for the line follower, and I had some readily available. Made it nice. Here are some of the scaling factors that I went through in my calculations for the 5-pole low-pass and high-pass Butterworth filters. The values gave me results that were really close to the theoretical and simulation results. I was kind of surprised. Now, as far as LT-Spice goes, we have the filter system simulated here. We have an upper cutoff frequency, so it's a unity gain filtering system. So minus 3 dB over here is at 16 Hertz, give or take, which is what I calculated for, and the lower cutoff is about 500 or 0.5 Hertz, which again is what I calculated for. This slide shows the high pass, low pass frequency attenuation. So we start here at 20 Hertz, and then we move down in magnitude to 200 Hertz, and that gives us a minus 99.48 dB attenuation, which is, it was to be expected at this point. And of course, we all know that we start off with a breadboarded circuit. Here is my first go at the circuit. So we have the sensors right here, and they go all the way across half the board. This circuit worked pretty well, especially considering that I had to stack, four electrolytic capacitors in parallel here and there. I thought it was going to be a lot noisier than it was. It turned out to be pretty good design, and it worked well. Here we have the actual output of the breadboarded circuit. As you can see, it's definitely a little chattery. It has some noise in it, but the pulses are a lot better than I expected, especially with all those capacitors. But yeah, it turned out pretty well. Unfortunately, I lost some of the images that I had for the frequency attenuation, but my actual design, I have those, and we'll be able to have a visual of those. And this slide shows the PCB layout in KiCad of the breadboard design. this provides a little bit more visual for how many components we use to get the values that I needed. Now some of the resistors are ran in parallel to achieve closer values to what we needed, and yeah, it's a lot bigger than it needs to be as well. That also is a factor. Now this is the first printed circuit board. This one is the direct implementation from the breadboarded circuit. Yeah, it's rough and primitive, I guess might be a good word for it. I taught myself how to program the LPKF machine on campus, and I printed this one out on my own. Now these traces in here, without the mask, it's really hard to solder, and you have to be very precise in what you're doing, because the solder can run off and hit the plate or hit the copper plane when you don't want it to. And if multiple components do that, then they're going to short each other, and it's really hard to tell what's going on. Here is a KiCad schematic of the second design that I implemented. A few change-ups. We got rid of some of the resistors that were tied in series, and I purchased some exact values for the capacitors. And yeah, I actually used 805, size 805 resistors and capacitors, which eliminated some of the sizing issues that we had. Furthermore, we have the PCB layout of the second design. So I went ahead and did a ground plane. You can see it here in red, kind of. But I had a ground plane, and I also implemented a bottom layer VCC plane, because I had trouble running all of these vias to where they needed to go. They were just running all over each other. So this is one of the easy ways to get the design finished, at least I thought. Now here is the finished second design after everything was soldered. What I did differently to help with the soldering issues and how precise you needed to be, I ended up milling some of the copper, or actually most of the copper, away so I can expose the pads a little bit better to where the pads weren't so close to the copper planes. Yeah, here's a great visual for the ground plane. The copper here that we see is the actual ground plane, and they are all grounded on the same. Here is the schematic, the KiCad schematic for my last design. This design is what I ended up sending to Oshpark to get professionally printed. So we see here we have the battery, so you have the positive 9-volt and rail and the negative 9-volt rail with the common ground in the middle. So I decided to implement an Arduino to feed the 5 volts to the sensors. So we have a 9 volts and ground going into the Arduino and a 5-volt power coming out. And the 5-volt actually powers the LCD as well. Finally, we have the PCB layout of my final design. As you can see, it's much cleaner. It's really tight together, but it's a lot cleaner. I had silkscreen sent to Oshpark, so they printed my name and the name of the project on the back. That's why it looks reversed right here. Over to the right, we have a 3D implementation that KiCad offers. Just offers a better visualization, and also the back layer is shown here as well. And you can see the silkscreen of the name of the project is back there as well. Here is the circuit that I received from Oshpark. As you can see, it is a lot more compact than some of the other designs. It was interesting, a great learning experience to do stuff like this with the 805 components. and the surface mount ICs as well. Another first for me was the use of solder paste. I had never done it before, and this was the first and only attempt so far. And I baked it in the reflow oven located in the Proto Lab on campus. And I feel that it turned out very well. There were no issues whatsoever with it. I mean, other than needing to go back and cleaning up a little bit, but the design worked out really well. So before putting the circuit in the enclosure, I went and grabbed some O-scope shots. So top left, we have the lower cutoff frequency, and it's very close to what I calculated for. So we have 588 millihertz, or 0.5 hertz, give or take. The top right, we have the upper cutoff, which is almost spot on to the simulated results of 16 hertz at a minus 3D attenuation. Bottom left is the unity gain of 900 millivolts, and here we have on the bottom right the maximum output that I was receiving. Now this is all before it goes through the ADC, so this is before any conversion. Here is a short video of the frequency being adjusted, increasing and decreasing to see the frequency attenuation. So as the frequency increased, we see a steep drop off and goes to 0 well before the 60 hertz noise that we are trying to account for. As the frequency decreases, you see it level out and drop off as well. Just for quick visual purposes, we have a 3D model of the enclosure and a 3D model of the clamps for the fingers that were used. These were 3D printed in the lab, in the Proto Lab as well. Here we see the my final design nested in the enclosure. We have a nest of 5 volts and 3.3 volts, and attached to an LED to let us know when the enclosure is on, or when the circuit is on, and the buzzer, which is attached to pin 10 and goes high for a certain range of values for your heart rate. So you have a buzzer every time your heart beats. And here we see the LCD actually attached to the enclosure, and that's kind of how it fits together. And you see the gain knob right here, the power LED, and the switches. Here we see the ADC. I chose a 16-bit ADC rather than the internal 10-bit of the Arduino. It provided me with better resolution, and there's actually built-in gain amplifier in this. So if I needed higher gain, which I did, makes it a little nicer. I was able to do so. Here's just another picture of the inside of the enclosure before everything is pieced together. Here is a close-up of the finger clamps that I used. Worked out really nice, other than the springs that I found in the lab were just a little bit too strong. So I opted to not use the springs because I didn't want to hunt, springs with the right force. But they served their purpose and they did well. Here's another quick visual, the 9-volt battery housing. It just made it really nice and convenient. You just open it up, pull them out. These are rechargeable, so the ones on the wall are charged. You just swap them out, and you're good to go. Here is a picture of the final design, just the front plate. Here's the gain, the adjustable gain, the power LED, the 2 switches for positive and negative rail, 9-volt rail. Here's the LCD display, which is in there loosely. I didn't want to glue it in or screw it in because I will probably be using that LCD for other projects. Here's a short video showing the project at work, and it'll have has a display that you can hear the beeping, and I was going to do beats per minute, but the algorithm proved to be a little bit more time intensive than I previously thought. But yeah, this is the end result. Alright, so we have a portable heart rate monitor. We have 3D printed clamps for the fingers with the IR, LED, and photo transistor inside of them. We have an adjustable gain, power light. We have power switches, one for the positive rail and one for the negative rail. I could have done it a little differently for better efficiency, but that's what I went with. We have the 9-volt casings. So it makes it easy to change the batteries once they die. Of course, we have the LCD display. I'm going to display the heart rate. So let's go ahead and give it a go. We'll power it on. Get my fingers in there really quick. Alright, so we have the beat going off every time the heart hits a certain range. So yeah, I was going to do beats per minute, but that turned out to be a little bit more time intensive than I originally thought, so I had to forego that. Yeah, so we can only have one right here, so I'm turning the gain up. You get a increase in the voltage and an increase for the maximum display, and yeah, this is the project. Thank you for watching.